going to do today is we're going to go through and talk about the logistics of the course, how you're going to get graded, what you have to do to get a decent grade in the class, and then we'll start talking about statistical mechanics. If you haven't found it yet, here's the URL. What we want to do is just sort of click through some of these links because they contain all the information for the course. That's what I'll do. So, I stole this from some beautiful work that's been done in the area of molecular dynamics. And we're going to be hopefully talking about molecular dynamics at the end of the course. And if you want to know more about this picture here, which depicts something called a conical intersection, sort of an esoteric concept, you can go to this paper right here. That's really all you have to do is if you click on this beautiful picture on the front of our website, it'll take you directly to this paper and you can read more about it. It might not make an enormous amount of sense until we get to the point where we talk about this subject later in the course. Okay, so the very first link on the website is something called announcements. Now, this is where I'm going to be posting announcements that I want to make in the class. I'm really not very good with Facebook, and I'll talk more about that in a second, which is the reason why I post my announcements to this page instead of doing something more intelligent, because I know you are all Facebook experts. But what I will do is I will post my announcements here. They will be in inverse chronological order, so the most recent announcement will be at the top, and then there will be a list of all the announcements that we made during the quarter, so you'll have sort of a record. If you miss some, you can just scroll down and find them. And I'll probably post an announcement or two almost every day. And so it would be a good idea to just check this, bookmark this link, announcements, and check it once a day or so to see if there's anything. Maybe I changed the homework assignment. Maybe there's some information about the quiz that's coming up on Friday. Maybe there's sample midterms. All of that stuff's going to be posted here on this announcements page. This is the syllabus. We'll go through this in a little bit more detail because this is kind of important. But the first thing I would like to impress upon you is that we don't want to print everything from this website. We don't want to carry around a folder that's got all of the links to this website. We don't want to print everything out, all the homework assignments. Right? Everything is going to be electronic in this class except for the quizzes and the exams. And virtually everything else will be electronic, and that's the way we want to keep it. We want to converge towards having a perfectly paperless course. We're not there yet, but we want to try and get there because ecologically it's a lot better. Okay, so please don't print every slide from every lecture and stick that in a notebook. That is a perfectly useless thing for you to do because these slides are going to be posted on this website until you are old people. Honestly, it's true. If you go back, the very first websites we created, like in 1995, all of that stuff's still on the internet. It never went away. So we don't need to print all this stuff. Let's not do that. Now, we're fortunate that we've got two lecture teaching assistants. Stephen Yapolsky. Stephen, are you here? Stephen's right back there. Stephen's an expert spectroscopist. He knows everything about the subjects that we'll be talking about this quarter. Don't let him tell you anything else. And Jean-Marc Johns, he was a TA for you last quarter. You were in 131B. Maybe you know Jean-Marc. He's back there. These two guys are going to be teaching all the discussions. I'll have more to say about them in just a second. Stephen's going to be moderating our Facebook site. The Facebook site's going to be important to you, but since I don't know anything about Facebook, Stephen's going to be the one who moderates everything that goes on there. So you'll be interacting with Stephen through Facebook and seeing him also in discussion. All right, we know when lecture is, we know where my office is. It's in SI2, room 2137. Everyone know where SI2 is? Yes. 2137 on the second floor. And it's in this hallway that's behind a set of doors, the purpose of which is to keep people from randomly walking in to these offices. but you shouldn't be discouraged from coming to find me. Right? This office is right in the front of the building. You can open that set of doors, walk down the hallway, find my office. The door is virtually always open. If I'm in there and the door is not open, it's because I've got like a cramped deadline or something. But most of the time, if you need to talk about something having to do with the class or the material, if you have a question about something, you can just come and ask me. We're also going to have office hours that happen sort of right after lecture. There's usually a shady chair in the park right outside this door where we can sit and talk. And so some of you I know will want to eat, and some of you will have other classes. But if you don't, and you have a question about lecture, what I've found is the best time to ask that question is when it's really fresh in your mind. You just heard it, you didn't understand it, you wanted some clarification. All right, so I'm going to try and sit over in that chair and answer my email, and if no one shows up for 5 or 10 minutes, I'm going to go walk back to my office and have lunch myself. All right, so if you need to find me, that's where I'll be right after lecture. This is the text. I know you all have it because we needed it for 131C. There's our Facebook link. The way we're hoping Facebook works, and the way it's worked effectively in the past, is that students talk to one another on this Facebook page and offer hints as to how to answer various types of questions, and it turns out to be very, very useful. Right? In other words, Stephen doesn't have to answer all the questions, although he will stir the pot and answer questions when he can, but you can talk to one another about problems, quiz questions, and so on, and answer each other's questions. And in the past, things have sort of automatically worked that way. It's a miracle, and so hopefully it'll work exactly that same way this quarter. That's what we're hoping for. This is the normal boilerplate that we always have to post. It has to do with adds and drops. You can read it. There will be quizzes almost every Friday. There's a quiz this coming Friday. And going back to the quiz system, if you had 151, we tried to get away from it. That was met with enormous resistance. I got a lot of feedback about homework in 151, and almost all of it was negative. So, moving away from that model. In this class, the problem is there really is no electronic homework option for us. In other words, even if we wanted to do electronic homework, there isn't any mechanism for doing it. And paper homework, logistically, is a nightmare in a class of this size to do well. And so, there will be assigned homework. None of it will be graded. No one will ever know if you do it, except that if you don't do it, the quizzes are going to be focused on trying to find out whether you did it or not. So it'll be helpful for you to do it. All right, we will usually have a quiz the first 20 minutes of each Friday, except when we quiz worth a lot, 200 points out of 600. There will be 7 quizzes, only you can choose the top 5. In other words, you can drop 2 quizzes for any reason. Right? If you're going to be gone, you don't need to talk to me. You've got 2 drop quizzes. If you completely blow a quiz, right, or sleep late, I don't know how long. You don't need to worry. You've got 2 drop quizzes, not just 1. Okay? We're going to average those. We're actually going to total those 5 quizzes to get those 200 points. Each quiz is going to be worth 40 points. Times 5 is 200. Boom. All right? Each quiz will be multiple guess. That might seem like a giveaway to you, but none of the above will be an option on every question. The questions, many of them, in fact, most of them are going to be numerical questions where you have to work out a problem, choose the right answer. If the right answer is not there, the answer is none of the above, and none of the above will be an option that we use. Okay? So these quizzes are actually quite difficult. Previous classes have told me it is non-trivial to do well on these quizzes. There will be 5 quiz questions, and what that means, as I'll explain in just a second, is if you miss 1, you've still got an A. If you miss 2, you've got a B. If you miss 3, you've still got a B. If you miss 3, you've got a B. 4, you've got a C. Okay, so you can afford to miss 1. You can't afford to miss more than 1. Most of you want an A in this class. Okay? Oh, here's the, I don't know why. Here's our Facebook. Here's Stephen's nice welcome statement. All right, check out the Facebook page when you have a chance. Okay, in addition to the quizzes, we're going to have 2 midterm exams this quarter. That's different from previous quarters. One on April 27th, one on May 25th. These are both on Fridays. They're going to both be in class. They're both going to be worth 100 points. They're both going to be completely problem-oriented. And I'll have a lot more to say about these later on. Finals on Tuesday, June 12th. That'll be comprehensive. It's worth 200 points. There are 6 discussion sections listed here. Here's where they're located. Here's who's going to be teaching them. You can go to 1, 2, or all 6 every week. No limit. The way these discussion sections will be structured is that Stephen and G and Mark are going to prepare a discussion study guide. Many of you are familiar with this concept from the classes that you had with me before, probably other profs. The discussion study guide has 3 or 4 problems on it that we consider to be central problems to the material that we covered or are covering during that week. Okay, so what will happen in discussion is they will take your questions on any aspect of the course that you have, right? Ask them any question that you want. If you run out of questions, we're going to work through this discussion study guide together, maybe in small groups, all right, and make sure that we understand how to do these key questions. All right, we're going to post these discussion study guides on the lecture page. You'll see where there's a link for those. So if you want to look at it before discussion, try these problems out, you'll be able to do that. All right, we're going to post the one for this week later on this morning. All right, we've been working on it this weekend. It should be done right about now. And so hopefully early in the afternoon I'll post it. You can look at it. If you have discussion tomorrow, you can be prepared for that. Okay, homework problems will be assigned on Monday of each week, blah, 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 blah. I'll show you the homework page in just a second. Your class standing will be continuously upgraded on the EEE website. Okay, and the way the grades are going to be assigned in the course, again, if you've had 151, you're already familiar with this scheme. You need to get 80% of the course points, which in this case is 480 points because there's 600 total course points. All right, you have to get 480 to get some flavor of A. I decide where the dividing line is between A and A minus, and I do that depending on where there's a break in the distribution. All right, but I guarantee you, if you get 80% of the course points, you're going to get some flavor of A. If you get between 60 and 80, you're going to get some flavor of B. Again, I draw the lines where it makes sense to draw them, but that's a hard cutoff between 60 and 80, 60 and 61. That's where the B cutoff is in C's, analogous, and so on. Okay? So in principle, everyone in this class can do well, and historically, everyone in this class, the vast majority of the people in the class, do quite well. I'll show you in a second. All right, exam regrading, academic dishonesty, these are unpleasant topics that we don't really talk about too much, hopefully. All right, lectures. Here's the lectures that I gave last year. You see how there's an asterisk next to each one of these lectures? So if you want to see what the next lecture is going to be about, you can click on this lecture from last year and you have a pretty good idea. Now, believe it or not, I take each one of these lectures and I try to improve them. So there will be a new and improved version of this lecture posted later on today. It won't have a star by it. It won't have an asterisk. That'll be the new lecture for this quarter. All right? I did make some changes. And so, but I am lazy enough to tell you that the lecture that I'm going to give you today is closely related to the one I gave last year, which I worked really hard on, by the way. Okay, here's the discussion study guide for this week. It's not actually posted yet, but it will be posted later on today. And in principle, there will be a YouTube video of this lecture, which is a new experiment that I'm doing. I find the concept very frightening. I'll post that over here if I continue to do this experiment after 1 or 2 lectures. Okay, Here's where the exams are. Notice that each quiz is listed. Here's quiz 1, week 2. Here's quiz 2, here's quiz 3. There's no quiz in week 4 because there's a midterm. Okay, so there's a lot of information on this page. Remind you what the quizzes are going to be. Here's the homework page. Homework 1 is to do all the odd problems in chapter 13. Here's the key. Right? Every problem's worked out. Click on this and you download a PDF of the key to your computer. Okay? Likewise for the other chapters. Here's all the homework we're going to do this quarter. It's a thing of beauty. Results, as we get them, they will be posted to this website. This will end up being a long table that looks a lot like this. Here's last year's table. All right, quiz 1, quiz 2, quiz 3. Here's the key to the quiz. Here's the grade book on which the quiz grade is tabulated. Here's the midterm exam key and so on and so forth. Every once in a while I post how am I doing? In which I work out what your effective course grade is, if there's some unusual weighting. In this case, I don't think there will be. In other words, you can just look at your course points, and if you're 80% or higher, you know you've got an A. If you're between 60 and 80, you know you've got a B, and so on. Here's what the histogram for the class is going to end up looking, in all likelihood, because this is how it looked last year. These are all A's. All right, see how this red line? That's the 80% line. I'm going to draw that right through the middle of a big group of students like this, because I'm going to promise you that if you get more than 80% of the course points, you will get some flavor of A. Right. The other side of the coin is if you get 79% of the course points, you're going to get some flavor of B, a B+. Okay, but I'm going to draw that line right at 80, I'm going to draw that line right at 60, and then these blue lines I draw. You see how there's a break in the distribution here? Boom. See how there's a little break in the distribution here? Boom. All right, I draw the lines between the pluses and the minuses. All right, seem fair enough? It's completely transparent. You might not like it, but you'll know how you're doing. All right, except you won't know necessarily if it's a plus or a minus. Okay, you ready? So I use PowerPoint. You all know that by now. I'm trying to get better at PowerPoint, so if you have suggestions for me, maybe you're really good at PowerPoint. You could say, you could do this, it'd be way better. I'm pretty easy to talk to. You can tell me that. I'm not going to be upset. All right, I would be happy to receive your criticism. These presentations post to our website 1 to 10 minutes before or after each lecture, usually after. Take notes, document with each slide. So not everything that you need to know is written down on these slides. I try to keep the slides free of a lot of text and clutter so that they're easier to understand. Right, so I'll be saying a lot of what you need to be knowing for each slide, and if I was sitting in your seat and I was taking notes in my notebook, I would write the slide number and then anything that you think is important, and then the next slide number. Each slide will have a unique serial number. This is slide 19, as it turns out. See, lecture 1, you see how the system works? That's supposed to be 19. This is supposed to be 1. You get the basics. So there's a serial number for every slide this quarter. Like if you want to come and talk to me in the park, I didn't understand something on slide 476. I can go right to that. We can talk about it, or we can both find it. That tends to be a useful thing to be able to do. Okay, so many of you know how my system works. I will talk at you in lecture, write these lectures, post all this stuff together. Stephen and Gia and Mark and I are going to write these discussion study guides. So you're going to be getting a lot of information from me. You're going to be seeing me for almost 3 hours a week. Then you're going to see one of these two guys or more. If you go to more than one discussion, they're going to be teaching the discussions. Hopefully, they will tell you the same stuff I'm telling you a different way. Right? They're going to tell you it in a way that makes more sense to them. What kind of stuff really makes sense to me, right? But here's another way to explain the same thing that I think makes a lot more sense. That's the whole reason why we have these guys teaching the discussions. They're going to put a different spin on the same material. That tends to be very helpful for you. Then you're going to do the homework, and that's the most important part of this process in terms of actually learning the material, doing problems yourself. By now, you guys all know that's the key to doing well in a class like this. And so hopefully we've made it easy for you to do the homework. We've posted solutions. The way to do the homework is not to look at the solutions and then go and do the homework. It's to attempt the homework, work really hard on it, and if you can't get it, then go look at the solutions. You understand all that, right? Okay, so Quiz Friday. We're going to get started with this craziness. Right, it'll only be 20 minutes or so, hopefully not too much longer than that. And we'll take it right at the beginning of class, so it's important that you be here right at the beginning of class. There'll be a stack of Scantrons in the back there somewhere. Pick up a Scantron when you come in. Please take just one, even though we're going to have quizzes all quarter. I would really appreciate it if you didn't take 10 Scantrons, because these Scantrons are expensive for us, and if that starts to happen, we're going to have to do something dumb like forcing you to buy the Scantrons yourself at the bookstore. I mean, we don't want to do that. Okay, we want to bring just the right number of Scantrons for the class each week. Right? So, please, take just one. All right. Now, I said I didn't know what the name of the class is, and that happens to be true, but let me tell you what's going to be in it, because that I do know. Here we are today. At the beginning of week 1, we got 10 weeks. Right, we're going to start off by talking about statistical mechanics and thermodynamics. So first of all, let me just back up and say, in 131A, you learned about quantum mechanics from Professor Renzettes. In 131B, you learned about spectroscopy from Professor Martin, namely. Right? In 131C, in principle, we have to cover all the rest of physical chemistry. Now, I'm sure that you agree with me that this is a foolish way to organize a 3-class sequence. And we understand that now, and we're going to reorganize this class in future years. But this quarter, we're going to cover everything else in this 131C curriculum. Right? And what that means is it won't be an in-depth study of all of these remaining subjects. It won't be. It can't be, because we don't have time to do it. But I'm going to try and convey to you what I consider to be some of the most important concepts. I hope you'll agree that there's cool stuff in this class, because I think there really is. Okay. So I know you started to do chapter 13 with Professor Martin, but we're going to go back from the beginning and work on this subject, okay? Because this is a super confusing subject, this statistical mechanics. Okay? We're going to stop by talking about that. If you read chapter 13 at the end of last quarter, great. Right? If you haven't, please read it now. Right? This is confusing stuff, and as I indicated, the quiz on Friday will be on the stuff sort of in the first half of chapter 13. Here's where the midterm is going to be. Notice that the midterm does not align with the end of this block right here. I may try to push this block back to the left, but in the past I haven't been successful in doing that. It's hard to shorten the subject. This happens to be a very important subject. A lot of courses have this whole 10 weeks dealing with this subject. That would be the appropriate way to teach the subject. You can't do that this quarter. Then we're going to talk about chemical kinetics. Again, this is a whole class. We are going to condense it down to just a few weeks. We're going to hit the high points, try to convey some of the main themes of chemical kinetics. And finally, underlying chemical kinetics is this subject called reaction dynamics. I'm not sure if we even got to this last year. All right? This subject tries to take up the whole 10 weeks. I will try and find room for this because it's important. It's important that you see some of this and understand what it's about, or at least a few concepts. Okay, and so here's where the midterms are going to be. The dates of these midterms are selected based on my travel schedule, it turns out, because I want to be here for as many lectures as possible. So on days when there's a midterm, I'm not going to be here. Those two guys are going to give the midterm exam. I don't think that'll present problems for anybody, right? But in terms of me being here and giving the lectures, that's absolutely the best way to do this. Any questions on anything having to do with the logistics of the course?
The quiz questions, would they be similar to the homework problems in the quiz?
Yes, they will. Will the quiz questions be similar to the homework problems? Yes, they will. What I will do is I will post some sample quizzes tomorrow or later on today so you can look at what quizzes look like, what quiz questions look like. I want you to get calibrated on that. Right, so those will be on the announcements page of our site, hopefully later on this afternoon, if not tomorrow. Any other questions? Okay, so what is statistical mechanics? Who invented it? What is it? Why do we need it? And how do we start thinking about this subject? Quantum mechanics was discovered in 1924. This is a timeline from 1800, there's 1900, there's 2000. Here's when quantum mechanics was discovered in a period of time, starting in 1924. And I know this is one thing that you understand extremely well after studying it for 20 weeks. These are the pioneers of quantum mechanics: Heisenberg, Schrödinger, de Broglie, Dirac, not shown here. All right, what does quantum mechanics tell us? Well, among other things, it tells us that if we assume a different confining potential for the electron, we're going to generate energy levels. Right? As soon as you confine the electron, you force discrete energies, allowed energies to be produced. Right? And quantum mechanics allows us to calculate what those eigenvalues are. Right? Also, to figure out where the electron is. We can calculate the complex conjugate of the electron spatial distribution. Right, depending on what that confining potential looks like. All right, so quantum mechanics taught us that there are discrete quantized energy levels in atoms and molecules. We didn't know that for sure before quantum mechanics came along. And in fact, all of the time before 1924, this would have been considered to be an extremely controversial issue. In fact, when were atoms discovered? Anybody know?
Discovered or talked about?
Proposed.
That one Greek dude, like splitting things up a bunch.
Well, there's an English dude named Dalton.
I know that dude. That dude?
There might have been a Greek dude.
Everybody Democrats, like they can only split it up so much.
Yeah. So Dalton was the guy who actually said, atoms. Atoms have got to exist based on all of this experimental data that we've got. The one thing that explains all this experimental data is atoms. 1806. Okay, did Dalton discover molecules? No. A guy named Avogadro proposed molecules. Italian guy. All right, later on in the 1800s, right about here. Right? And did everyone just hear about atoms and molecules and buy into this concept? Lock, stock, and barrel? Not at all. Right? The existence of atoms and molecules was controversial during this whole period of time here. Right up until Einstein observed Brownian motion in 1906. It's right about here. All right? Everybody know what Brownian motion is? You know, how many people have looked through an optical microscope at a bacteria? Right? You know how that thing wiggles around when you're looking at it? It's jiggling, right? That's Brownian motion. What it is it's collisions of atoms, molecules with the bacterium, and that object is small enough so that those collisions are not isotropic in terms of the perimeter of the bacterium. There's more waters hitting it one direction, and then more waters hitting it another direction. And so it jiggles based on this influence of these collisions. And when that was observed by a physicist named Brown, of course, Einstein correctly interpreted his observation. He said, what's happening is atoms molecules are colliding in an anisotropic way with this tiny microscopic object, and that's the source of these fluctuations, and that was the only explanation that made any sense. And so right up until 1906, this subject was discussed in scientific meetings. All right? There were the so-called positivists who believed in the existence of atoms and molecules. All right? This was considered a controversial issue for almost 100 years. That's pretty amazing. Right? What's really amazing is that in the middle of this controversy, all of these guys together figured out statistical mechanics and thermodynamics. Right? And as you'll see, knowing that discrete states exist is absolutely essential to really putting this construct of statistical mechanics together. If you don't have states, it's hard to think about statistical mechanics, which has something to do with the occupation of these states, the statistics of that. All right, so it's astonishing, really. I mean, atoms are discovered here, molecules are proposed somewhere around here, and here, there's just this vitriolic discourse that's going on. In the middle of this, these guys put together thermodynamics and statistical mechanics. Really quite extraordinary. These are the guys mainly responsible for the statistical mechanics part. Maxwell, Boltzmann, Gibbs, those are names that you probably know already. Here's Maxwell. This guy was a genius, Scotsman. Maybe one of the less important things that he did was contribute to the Maxwell-Boltzmann distribution. He actually derived Maxwell's equations, which are unbelievably important. He invented three-color photography, it turns out, right, in his spare time. Right? Theory of compound colors. Like, he did the first three-color separation, right, to generate a photographic image, and here it is. Right? This is a ribbon, a Scottish tartan, it turns out. Appropriate, because he's Scottish. He told the photographer how to do this. 3 filters, 3 photographs, all 3 of them black and white, RGB, red, green, blue, filters, put them together to generate a color rendering. This is the very first color photograph. Right? Maxwell did that. Guy was full-on genius. Boltzmann, cantankerous character, volatile, prone to depression, eventually hung himself when he was 62 years old because he got so depressed at one point in time. Depression is a terrible disease. Maxwell-Boltzmann distribution, right? Pretty central to thermodynamics and statistical mechanics. S equals K log W. How many people have seen that equation outside of the license plate at Professor Tobias's Prius? That's his Prius with it. K log W. Don't put it into his car. And this is his grave in Vienna. S equals K log W. In case you're wondering, that was his idea. Willard Gibbs, one of the first great American chemists. All right? This guy's an Austrian. This guy's a Scotsman. All right? It's nice to have an American make an appearance. All right? We don't hear about any Americans in quantum mechanics. It's all Germans. De Broglie, French guy. Gibbs, right? Entered Yale when he was 15 years old. Stayed there and got his PhD. True story. Got the first PhD in chemical engineering in the United States. In, do I have it on here? Something like 1863. Stayed there, right, as an unsalaried professor of mathematical physics. Just worked there. This was not uncommon at that period of time. If you hadn't published papers, you could still get appointed as a professor. They just wouldn't pay you anything. Or you had to work your butt off, teach classes, do research, but you got paid nothing. This was not uncommon in the U.S. and Germany at this time. But eventually, he worked out installed thermodynamics during this period of time when he was unpaid, and Johns Hopkins offered him a $3,000 a year salary, and so then Yale countered with a $2,000 a year salary. And he took the job. He stayed at Yale. Right? His family was there. He loved New Haven. At that period of time, if you've ever been to New Haven, well, let's just say it was a nice town in those years. And he died in 1903. So this guy was one of the first great American chemists. And he's buried in the famous Grove Street Cemetery. If you're ever in New Haven, Connecticut, visiting Yale for some reason, maybe you go to grad school there. This is a beautiful cemetery that dates to the late 1700s. You can go in there, you can find his tomb. In fact, Grove Street Cemetery is one of the few cemeteries that has a great website. You can put anybody's name in here, right, that's buried there, and it'll show you their gravestone. It's pretty cool. Okay. Why do we need statistical mechanics? We've got thermodynamics. We can calculate things about bulk amounts of molecules using all the thermodynamic information that we can look up in any CRC handbook. Right, why do we need statistical mechanics? Right, what does that bring to the table? Here's a Wikipedia piece of a Wikipedia page on ammonia. All right, standard enthalpy change of fusion, standard enthalpy of formation, heat capacity, standard enthalpy change of formation, standard molar entropy. So we can look up all these numbers and use them, right? And that's what thermodynamics is all about, right? Is how to parameterize the physical behavior of substances. The problem is it makes no connection to the attributes of molecules. In other words, I can look at this number here, heat capacity, but there's no way for me to calculate this number starting with the molecular properties. For example, methane, CH4. Right? I know what the structure of methane is. I know what the bond distances are. I know everything about that molecule. I can measure spectroscopic properties, but I can't calculate anything having to do with the thermodynamics of that molecule from thermodynamics. Thermodynamics doesn't give us the tools to do that. Statistical mechanics builds that bridge. Right? It allows us to go from the properties of ammonia, bond angles, bond distances, number of atoms, number of normal moles. It allows us to calculate these numbers from these molecular attributes. That's the key. And I think you'll agree that's an amazingly important thing to be able to do. All right, we can take the molecule, we can learn about its structure, and then when we're done learning about the structure, we can calculate the thermodynamic parameters from that. All right, we want to learn how to do that. That's really, really important. This is one of the first papers where that was done for ammonia back in 1939 by these two guys. All right, and here's the equation that we're going to be familiarizing ourselves with later. And the important thing in this equation is a parameter called Q. This is something called the partition function. It is the central construct in statistical mechanics. Right? Q is the key. If we can understand Q, we can understand this link between molecules and their structure and thermodynamic variables. Right, we're going to be getting to that. We want to really get to the point where we understand Q in some detail. Now, to teach this stuff, I use a really great book by a guy named Leonard Nash. Can you see how thin this book is? It is a thing of beauty. Right? It is perfectly concise, easy to understand, and it explains this really esoteric subject in a clear, understandable way. And so, how many of you hope to have a career in science or engineering? I hope by now. That's a lot of you. You appreciate the fact that you can't find all the information that you need on Wikipedia. It's not there. Right, some of it's wrong. There's a few key books that you ought to have in your library. And this is one of them, partly because it costs like $4. All right, it's down here on my list of all-time greatest hits. Okay, buy all of these. Use the course. I mean, don't buy any new books. All right, but these are all irreplaceable, unbelievably valuable books that you will use throughout your life. Every time you have to, some subject you're reading something in Science magazine that you don't understand in the area of biochemistry, you open up this book right here. It's in there. All right, you know what I'm talking about? So this is one of these gems, right? There's no replacement as far as I'm concerned for this book, right? It is special in terms of how clear it makes this explanation of statistical mechanics. Okay, now we're not going to finish this lecture, but let me just tell you, let's get started. I think you guys recognize this as a Morse potential, right? These are the bound vibrational states of this molecule. Here's the harmonic approximation to that potential. I'm not telling you anything that you don't know. Everybody knows about vibrational spectroscopy in this room, am I right? Now, we can approximate this green guy here with this ladder right here. Right, this is the V equals 0 state. That's the ground vibrational energy level. 1, 2, 3, 4. Okay? And so we can talk now about a three-dimensional array of molecules. Here, this is my short form notation for a molecule. Let's just forget about the 0 point energy for now. All right? There's an energy level, there's another one, they're evenly spaced in energy, and there's three molecules here, A, B, and C. Right, that's what that denotes. Okay, so now if this system of three molecules has 0 energy, our energy level diagram looks like this. Yes, if it has 0 energy, then all three of these guys have to be 0, and right, we're neglecting now the 0 point energy. Right, let's just call V equals 0 to 0 for energy in this system. All right, everyone agree? That's the only molecular configuration that it's going to add up to 0 energy for molecules A, B, and C. There's no way for any of these other energy levels to be occupied, otherwise the system will not have 0 energy. Now let's consider the case where we've got 3 quanta of energy distributed over 3 molecules. All right? How can we do that? Well, we could put all 3 quanta into one molecule. Put it in A, put it in C, put it in B. All right, that's one way to distribute these 3 quanta of energy across these 3 molecules. Put all the energy in one molecule. There's 3 ways to do that. Another way to do it would be to put 2 quanta energy into one molecule, 1 into another, 0 into the other, and it turns out that there's 1, 2, 3, 4, 5, 6 different ways to do that, if you work it out. And here they are. Right? That's 2 quanta into one, 1 quanta in the other, and 0 in the other. That adds up to 3, and there's 6 different ways to do that. And finally, you could put 1 quanta in each of the 3 molecules, and there's really only one way to do that. I think you can see intuitively. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ways to put 3 quanta of energy into 3 molecules. Everyone agree? So we're going to refer to each one of these guys, that guy, that guy. These are microstates. That's what we're going to call them. There's one there. There's one over there. Here's one down here. All right, there's 10 of these guys. 10 microstates. Now, there's 10 microstates, but there's only 3 configurations of microstates. 3 configurations. It's easy to see that these 10 microstates exist in just 3 configurations. This notation will use specify configuration. See this? Does this look confusing and cryptic? No. It's easy to understand. That's the number of quanta in V equals 0. Right? That's the number of molecules in V equals 0. 2. 2 here, 2 here. These are all the same configuration. So if that's 2, that has to be 2, and that also has to be 2. That's the number of molecules in quantum state 1. 0, 0, 0. Quantum state 2, 0, 0, 0. Quantum state 3, 1, 1, 1. All right, so this guy is 2, 0, 0, 1. Boom. That's his configuration. You with me? Look at this guy. 1, 1, 1, 1, 1, and 1. So that's a 1. 1, 1, 1, 1, 1, and 1. That's a 1 right there. And 1, 1, 1, 1, 1, and 1. That's a 1 right there. And then 0. That guy describes the configuration of all of these. Okay, so we've got this shorthand notation that we can use for the configuration. This guy is 0, 3, 0, 0. Boom. Okay, now I haven't said anything profound. Okay. Now, we need to count the number of microstates associated with each configuration. Is there a formula that we can use? In other words, are we going to have to go through the exercise of making these diagrams where we've got Avogadro's number of molecules? That could be tedious. All right, we need a formula. Can we derive a formula that allows us to figure out something about these microstates? Starting with the first, 2 quantum increment. Okay, so let's look at this guy. All right, let's say I want to put a 2 quantum, I want to occupy v equals 2. All right, I can put him there, or I can put him next to into B, or I can put him into C. In other words, there's 3 ways that I can put that first quantum, that first v equals 2, into these 3 molecules. It can go to molecules A, B, or C. Then, if I choose A, there's only 2 places left over where I can put the next 1 quantum of energy, then the second 1 quantum energy can go either the remaining 2 molecules, and finally, the 0 is going to have to go right there into molecule B. Right, that's the last parcel of energy. So this system has 3 quantum energy, all right, and the number of ways to generate this is 3, right, 3 different places to put that first quantum, times 2 different places to put that second quantum, times 1, only 1 remaining place to put that last quantum. Right, 3 times 2 times 1 is 3 factorial, that equals 6. Boom! That correctly predicts the number of microstates for this configuration. 3 factorial. Now, let's try the same thought process with configuration 1, where there was v equals 3, starting with the 3 quantum increment going into 3. So we could put it in A, B, or C. Right, we chose A here. Then the next increment of 0 could go in. So the next 2 are going to be zeros. We can put the first 0 here or here. Right? It's got to go in the remaining 2. Okay, and so if we start here, we can put the 2 zeros here. If we start with B, we can put the 2 zeros here. The difference is that there are 2 verbally distinguishable ways to put these 2 guys into the molecule. I can put 3 quanta into A, and then I can put this guy into C, and that guy into B, or I can do it the other way around. Right? I can put B in first, and then C after putting A and 3 quantum energies into A. All right, so we have to adjust the number of quantum states here by a factor of 2 factorial, it turns out, because there are 2 verbally distinguishable ways to insert these 2 guys, or these 2 guys, or these 2 guys. That one go in first and that one go in second, or vice versa. All right, when we make that adjustment, we're going to have 3 factorial divided by 2 factorial, or 3 possible microstates. Configuration 3, that's this guy, where we had all 3 of these guys in quantum state 1. All right, starting with the first increment going into the 3 molecules, the second one going to remaining 2, third one going to go remaining 3. But there are 3 verbally distinguishable ways. Right, so it's 3 factorial divided by 3 factorial, or 1, and boom. There is only 1 state. Okay, and so this is our equation. The number of microstates W. That's n factorial. N is the number of molecules. That's the number of states occupied in 0. Number of molecules that have 0 quantum. Number that have 1. Number that have 2. And so take this random example, plug those numbers in to our equation, and you get 168 microstates for this guy. I think you would have to agree it would be messy to work that out. And I'll come back. We're going to do this again on Wednesday. So if you didn't get any of that because I went fast, don't worry, we're going to do it again on Wednesday.